one of the most fascinating questions in cosmology today is what is this stuff, this 90%, maybe 99% of the stuff in the universe that we think is around but don't see. This problem of dark matter.
This problem of the dark matter is a fascinating development that has been known for 50 years. Astronomers have been saying for more than 50 years that there seems to be dark matter in these clusters of galaxies. There's dark matter in the outer regions of normal galaxies. And now the idea that this dark matter dominates the total mass density of the universe, perhaps accounting for 90 or 99%, is what many people call the ultimate Copernican revolution, that we're not even made of the dominant material which comprises the universe. The Copernican revolution, of course, refers to the notion, first really argued strongly by Copernicus 400 years ago, that the Earth is not the center of the universe. The stars don't revolve around the Earth. The sun doesn't revolve around the Earth. It's the other way around. The Earth revolves around the sun. Now we know the sun is just a very minuscule speck on the outskirts of one galaxy, and there are millions and millions of galaxies that we can see out there. So we are clearly not the center of our universe. But we used to think that we were made of the most dominant stuff of the universe. Our atoms were the dominant stuff, the hydrogen, the helium, the oxygen, etc.
So how do we know? Because, okay, first maybe there are two questions. How do we know that there is something dark if we cannot see it?
That's the first question. How do we know, what is the evidence that there's dark matter at all? The evidence has to come through its gravitational effects. We use the laws of Newtonian mechanics that have been around for 300 years. Those are the laws that govern the orbit of planets around our sun.
So we see stuff going around spiral galaxies?
We see stuff going around spiral galaxies. It turns out that we can measure the light in the galaxies, and we have a fair estimate of the mass of a star.
So, and we can measure the velocity of these clouds?
That's right. We can see the velocity of clouds, and we know, for example, in the solar system, that we are orbiting the sun at 30 kilometers a second, and if we were 4 times further away from the sun than we are, we would be orbiting at half that speed, 15 kilometers a second. This is known as Kepler's law, that and just as a simple relationship of Newtonian mechanics, that if you're away from a star, your orbital velocity falls as the square root of the distance. But in a galaxy, it's a more complicated situation because the mass is not concentrated in a central star. It's spread out over all the light of the galaxies.
Well, it's basically the equilibrium between centrifugal force and centripetal force,
and the gravitating mass.
Yeah.
And when we do that calculation, we would say that the rotation of the outer regions of the galaxy should be falling with distance from the center of the galaxy. But they never fall with distance. All the galaxies that we've observed, and it's quite a few now, many, many dozens, every one of these galaxies has a rotation curve, that is to say rotational velocity as a function of distance from the center, that is flat with distance, as though there were a dark matter component in that galaxy whose density was declining with distance, such that the total mass of the galaxy is not converging. As you add up bigger and bigger shells, the mass continues to grow linearly with distance.
Even though we cannot see any stars.
We can see nothing. It's clear it's not stars. It's clear it's not ordinary gas. It's not ordinary. It's something that is very highly invisible. It doesn't appear to be ordinary matter.
So this seems to be true for our own galaxy. This seems to be true from many of the spiral galaxies that we can measure.
That's right. On any system that the astronomers try to measure mass on scales larger than, say, the distance of us to the center of a galaxy, 20,000 light years, any system that large or larger always seems to be dominated by dark matter.
Even the elliptical galaxies seems to have also some dark matter. We can measure globular clusters smaller.
That's right, and we can measure the confinement of their hot plasma, which seems to be confined in a way that's inexplicable unless there's dark matter.
And we see this hot plasma because of the X-rays that they emit. And,
that's right. So, and we see in clusters of galaxies, we see two different lines of evidence to suggest dark matter. In Zwicky, Fritz Zwicky, a famous astronomer 50 years ago, said...
That was the first one to
The first one to talk about it, well before its time. He said that the galaxies in the Coma cluster of galaxies, a very rich agglomeration of 1,000 galaxies.
Yes, there's 1,000 galaxies.
1,000 galaxies or so are moving around much too fast to be held together by their own self-gravitation, because he could calculate the amount of gravitational attraction of all the material there, assuming the stars made up the total mass.
We're similar to the sun. And
it was wrong by a factor of 50. I mean, as though 50 times more mass were needed than appeared to be present in the stars. I mean, this is a fairly astounding discrepancy. And he said, I don't understand why this cluster exists. It must have some unseen form of matter. And now the evidence is confirmed in many different experiments. There's unseen matter. Now, but your question of...
But you spoke about a second evidence, which...
Oh, the second evidence, right. Well, that's called a virial analysis of the galaxies orbiting in the cluster. The other evidence is the nature of the X-ray emission. Again, this hot plasma, which is confined in the cluster, emits radiation. And by mapping its density distribution and estimating its temperature distribution with some simple equations, we can show that this provides an unambiguous estimate of the mass. Again, coming up with a very high mass, much higher than is given by the stars.
I think there is a further, actually, piece of evidence in the clusters of galaxies.
Oh, I guess there's the lensing.
The lensing.
Right.
Yes, the arclets, the fact that we can measure the mass of the clusters by the amount of bending that it gives on the galaxies which are in the background. And there, again, we obtain very similar results than with the velocities of the galaxies and the temperature of the X-ray gas.
Now, this question, though, about the nature of the dark matter, I guess we should think about what is the argument that says that the dark matter can't be rocks or something that we just too small to shine, but just ordinary material that's compressed, like snowballs or something of that sort? Why do we think it's not the stuff that we're made of?
We're not sure. Okay, that's really maybe the first answer, but we have a pretty good idea of how many protons and neutrons there are in the universe. This is a so-called nucleosynthesis argument. One of the major confirmation of this general picture of the hot Big Bang is that we can compute the amount not only of hydrogen, but the ratio between the hydrogen and helium, the deuterium, the lithium-7, which has been produced in the Big Bang. And we have only one parameter to fit a large number of data, and this parameter is just the amount of baryons and the amount of protons and neutrons. And if the best fit to all the data gives 5%, something like that, 5% of the critical density.
Critical density
is in baryons. The critical density is this density of the universe where it just expands forever and just coasts at infinity. If it was slightly more massive, it would recollapse.
Slightly denser, it would recollapse. Slightly less dense, it would expand forever.
Yes.
So this is the boundary line.
The boundary line. So about 5% of the critical density is in protons and neutrons, what we call baryons. And really, it depends how much dark matter there is. I think the current situation of the community is the following. In the last 10 years, 5 to 10 years, we have witnessed an amazing consensus building up on the existence of dark matter.
Right.
We are left with two problems. One is how much there is exactly.
Yes.
And what is its nature. How much there is exactly is this old question in cosmology of measuring the average density.
Right, whether the universe is at the critical density or below the critical density. We don't think it's above the critical density, but a lot of the direct evidence suggests it's below the critical density.